Okay, we're gonna do a quick warm-up, and I would like you guys to do all of these. Write an equation for an antiderivative of each function. Remember, plus c. Give it a try. What would make cosine? What derivative of what function is cosine? That would be sine. If I took the derivative of sine, I would certainly get cosine. But you have to leave room for the possibility that you might have had some kind of constant, because constants go away. Every time you do an antiderivative, every time you do one of these bad boys, you have to consider the fact that the answer might have had originally a constant that just turned out to be 0. Alrighty, so for sine of 2x, you have to be a little slick, because cosine, it would be negative sine. So to get rid of the negative, you would have to put negative cosine. So the negative cosine would be positive sine. Of course, there would be a 2x here, but remember that if you were to take this derivative, you would have had to deal with the chain rule. At the end, you would have multiplied by 2, but you don't see a 2 here, which means that you probably want to cancel out that 2 by attaching a 1/2, and then plus c. Let's try it out. Let's see if that's true. So if you had negative 1/2 cosine of 2x plus c, what would that derivative look like? So first, the negative 1/2 is on the outside. We don't want to deal with that yet. But for the cosine, you would have ended up with negative sine of 2x. And then you would have had to multiply by the derivative of the inside, which is 2. Now, if you actually, and by the way, that constant, that would have gone away when you take the derivative, right? Alrighty, so that 1/2, that negative cancels out with that negative, that 1/2 cancels out with the 2, and that constant that we had right now, if you would have done the derivative of this should have equaled to 0. The derivative of oh, my pen, come on. So any constant, the derivative would equal to 0, and what do we end up with? Sine of 2x. So yes, this is the way to properly write the derivative, the antiderivative of this guy right here. Now this one right here would be very difficult if you don't already know some identities. I do happen to know that the derivative of a tangent would end up giving you secant squared. So I know that the antiderivative would be tangent. But what am I missing? What am I missing? Because if I take the derivative of this, I would end up with 3 times secant squared. So I would have to multiply by 1/3. So this would be the antiderivative. If you take the derivative of this, the 3 will cancel out the 1/3 via chain rule. And we would end up with secant squared of 3x. Cosecant squared of 4, that would be, I know that the derivative of cotangent is cosecant squared, but I also know that it would actually be negative. So the derivative of cotangent is actually negative cosecant squared. So I would have to put a negative, so the negatives would cancel. Also, we have a 4. So we would end up with a 4 at the end, so to cancel out the 4, we will probably need a 1/4. So if you would take the derivative of this guy, you would end up with cosecant squared. Pretty much just start small. Just realize that cosecant squared correlates with cotangent, and then you make the realization, oh, the derivative of cotangent would be negative, so let's put a negative up front to cancel out that negative. Oh, there's a 4, let's put a 1/4 to get rid of the 4. Boom, and then you end up with a final answer that looks like this. And then the last one is not that bad either, because you just have to remember whose derivative equals secant tangent. Oh, did you by any chance say secant? Oh, if you said secant, then you are correct. Derivative of a secant is secant tangent. But there's a 5, so let's put the 5 here. And that's actually all we had to do. If you take the derivative of this, you should end up with 5 secant x tangent x. And we're done. Let's move on. Alrighty, so over here we have some definitions, and most of them you already know. I mean, at this point, just write this down if you didn't already know this. But If y equals f of x, then the inverse would clearly be x equals f of y. You just flip the x and y's. If the inverse relation is a function, then f is said to be invertible. Sometimes we end up with an inverse where the function wouldn't be. If f is invertible, then you can write the inverse function as this. And if f is invertible, then this equals that. And then the last property, the graph of f and f inverse are mirror images across the line y equals x. Alrighty. Now, you know what this is, right? Let me just, you see that if you took a function, which is, let's say, let's go ahead and say, let's do some easy. I can't come up with anything easy. Okay. X squared. I'm not going to say x squared plus 4 because then you have to do like subtract 4 and then take a square root. But let's say y equals x squared. Then that's another way of saying f of x equals x squared. I digress. But the inverse will be if you were to flip those. So that's like x equals y squared, and then you have to like take the square root on both sides, and then y equals plus or minus square root of x. Well, if you for one, this is not a function, so this was not invertible. But let's say it was invertible. If you, by the way, this is now f to the negative 1 of x. But this is not invertible because I know that this kind of looks like this, and that's not a function, doesn't pass the vertical line test. But if you plug this into here, you would end up with square root of x, plus or minus doesn't matter, and then you would end up with x. So that's pretty much what this is saying. So I hope that's kind of clear. I felt like I should have spent some time to just kind of talk about it real quick. So you plug an inverse into itself or vice versa, you should end up with x. Meaning that if I would have taken this and plugged it into here, same result, except we would have had plus or minus x, and clearly that's not a thing. But then again, our property only works if it's invertible, and this was invertible because our inverse looks like this, which is not a function. Anyways, doesn't matter. So that's what that means. So let's talk about the definition of inverse trigonometric functions. So what does the inverse sign mean, or arc sign? It means that you pretty much, what do you plug into sine in order to get a certain value? Or what has to be plugged into sine to get a certain value? So for instance, sine inverse, you might want to know, oh, how do I get 1, right? Instead of plugging in values into sine, you think to yourself, how do I get 1? Then you, what must go into sine to get me this 1 value? And then you can pretty much find the stuff, in this case, pi over 2. So traditionally, values like pi or pi over 2 would go into sine. But if you're talking about the arc sign, you put values that happen to be between 1 and negative 1. And I totally miswrote that. But you pretty much are trying to find out how to get these values. Like, how do I get 1/2? Right? You put that into arc sign, it tells you, oh, if you put this degree into sine, then you would get 1/2. So the arc sign pretty much reverses the process. Let's talk about a function real quick. Let's say this is a function. And the way a function works, function, smiley face. Oh, here we have a sun. Alrighty. When you plug in one thing into a function, you should get one thing out. You could actually plug in two things and get one thing out. So the sine by itself is a function. Because for a sine, we can put, let's say, negative pi, 0, and pi, and this would still all give you one thing. It would give you 0. So sine is fine. Sine is cool. Sine is amazing, right? But if you were to reverse the order, if you were to, let's move this up a little bit. This right here is my inverse, right? Suddenly, you plug in the 0, and you can have all of these infinite numbers of ways that sine could have given you 0. That's not a function. So even though this will be the inverse, this is not a function. How do I say not a function? Do I use red? No function. Alrighty, so the sine is a function. It would totally, sine looks like this. It would totally pass the vertical line test. But inverse sine isn't. Inverse sine simply isn't. So we kind of have to create a range for it in order not to get repeating numbers. We don't want this situation because sine could give you an infinite numbers of ways to give you 0. So we kind of narrow it down to like a certain region. So for instance, sine kind of looks like this if you narrow it down from negative pi over 2 to pi over 2, and over there it's kind of nice. It doesn't repeat. For instance, if I do like a vertical line test, which is what an inverse really is, it would pass that. But the moment I would go past pi over 2, it wouldn't. You can see that over here. We wouldn't. If he went further than negative pi over 2, it would start failing the horizontal line test. The horizontal line test is a vertical line test for inverses. So that's why we have to create these ranges. So if you're wondering why we have these ranges, that's why. Because function. Back to this. Watch this part again, please. Like whatever I just talked about functions is kind of important for math analysis. So just pause the video, go back, just listen to what I said before. I know I speak halfway German and everything I say is hard to understand as it is. And but just do it again, okay? It makes me feel better. Cosine inverse is, let's plug in the y into the x, and let's plug in the y into the cosine and see what we would end up with. So if you, what would make cosine equal 0? What would make cosine equal 1? What would make cosine equal -1? Stuff like that. And then tangent inverse, so what would you have to plug into tangent, you know, so you flip that. So that's pretty much just this basic definition. So what arc sine, arc cosine, but just by the way, I should talk about this. Cotangent, by definition, is 1 over tangent, right? So that's a fraction. We don't want tangent to ever equal 0. So in this range, is tangent ever 0? It is 0 at 0 and pi, which is why they're excluded. And since they're excluded, we're fine. We don't need to make a statement. But when it comes to secant inverse, secant is 1 over cosine. Cosine is 0 at pi over 2. That's a problem. So we say x cannot equal pi over 2 inside this range. And cosecant is 1 over sine. Again, sine is not allowed to equal 0, and that's when sine equals 0. So that's a no-no. That's a boo-boo. That's what we call a boo-boo in the math business. Alrighty, so this right here are just little definitions. By no means should you ever think that the arc sine is the same thing as cosecant. I don't know why I connect. This is actually the arc cosecant, so that doesn't matter. No way should you think that, why I'm putting a negative, that the sine inverse has anything to do with the cosecant. Why can't I write anything? How do you write cosecant? Cosecant of x. Jesus. Alrighty. No way can you make this connection. This does not equal one another. That's bad. That's bad. Right here, arc sine means reverse the x and y's, where cosecant means 1 over sine. Okay? So those are totally different things. So in regular algebra, there's a correlation with like the -1 sign when you have something to a -1 and it being an inverse, but not for sines and cosines. So do not make this mistake. I used to make that mistake, and I'm great, so I'm assuming that you would make the mistake as well. Let's move on. Okay, some more definitions for you to look at, and if you take the derivative of the arc sine, that would be 1 over the square root of 1 minus x squared. And then the good thing is when you do the arc cosine, it's like the same thing, except in the negative. That is the greatest. I love it. And then when you do the arc tangent, that's a plus sign instead of a minus without square root. And then the cotangent, for same reasons, which I don't even know why these are similar, boom, just a negative. And then for the secant, it would be whatever this is. That looks so weird. And then for cosecant, you do this. And your graph must be in radian modes. That makes sense. You know, I don't know why. And then the derivative of each. Don't bother with this. Memory aid. We don't need memory aid. We are the memory. Alrighty, differentiate arctangent. Just know what the definition said, and boom, we got it. Differentiate secant. Just kind of look at what your memory tells you, because we are the memory. And then when you're trying to differentiate this one, we have a chain rule to follow. Chain rule. Just Amazaki just walked in. He just threw me off a little bit. Alrighty, so arc cosine would give you this, but because we're talking about a chain rule, you have to take the derivative of whatever is inside, and 7 times 5 is 35, and then that would be x to the 6th. And if you simplify, it looks something like this. Over here, again, we have another chain rule, so you would just do it the way you would usually, but just multiply by 7 at the end, which is why we get this. And I think that is, yeah. Oh, by the way, you can simplify this, because you should have ended up with 7x squared, which is 49x squared. And then another chain rule. So let's go with this one. We have 7x squared, which is 49x squared. And then we have 1 over the f's value, whatever. But then, because it's chain rule, multiply by the derivative of 7x, which is just 7. And then these are the last ones. Let's talk about them real quick. I'm not going to do them, we're just going to talk about them. The videos are long enough as it is. If you take the derivative of this, it's just a chain rule, so do the regular thing, which I believe was 1 over, negative 1 over 10x squared plus 1 or minus 1. And then multiply by 10, whatever that is. And then for this one, what is this? What is this? Oh yeah. It's 0.5. Alrighty, so that will be just extra 1/2 chain rule. If you do the chain rule, that's going to give you this bad boy, you know. So just make sure you multiply by that on the outside. And then, okay, that's my cue. We're going to stop the video right here. I'm going to expect you guys to do these problems in the video. So go ahead and just do them all, and we'll talk about them. The hard ones are already solved for you. Merry Christmas.